Hello, a very warm welcome to this talk on Why Maths. I'm Francis Hunt from the Further Maths Support Programme in Wales, and we're based, as it says, at Swansea University, and our website is reasonably easy to remember because it's just furthermaths.wales. So, who are the Further Maths Support Programme? Well, we were set up in 2010 by the Welsh Government. They were concerned that too few students were taking A-level further maths and so gave us the job to promote and support it. Now the graph down here on the left shows the proportion of A-level maths students who also take A-level further maths. Wales is the blue line here in the middle and England is the red line here at the top. And you can see that since 2010 the proportion has risen from about 7% to about 16%, just overtaking the proportion in England. So with the help of teachers and students like you across Wales, we seem to be succeeding in our mission currently. On the right here is a photo of a typical workshop, one of a number we run for both students and teachers, and I'll tell you more about the sort of things that we do which you might be interested in at the end of this talk. Now, disadvantage of a video talk is I don't exactly know who you are, so I'm assuming that you are at the point of deciding what you want to do in possible future studies. And my promise to you is, as it says here, by the end of the talk, you'll know why taking maths further is a great idea for you. We'll do this by answering three questions. So question one, in which jobs will maths help you? In which jobs will maths help you? Well, that's easy. The answer is almost all. And here's a slide to show you some of the more mathematical ones. If you want to pause the video and read through some of them, please do so. We'll look at a few of them in more detail. Well, you're not going to be surprised that a mathematician uses maths. But what do working mathematicians actually do, and why do they do it? Let's hear from some of them. Here's Hannah Fry. At the time of making this video, she's the president of the Mathematical Association.
I think I've always been quite mathematical, if I'm honest. I think when I was at school, I really liked doing maths because it was almost like having puzzles. I liked the idea of learning a set of rules and then trying to find the answer in a set of problems that you knew how to solve, but just the route to solve them wasn't necessarily completely clear. And then as I progressed a bit further and understood a bit more about what mathematics is and what it's about, I really became attracted to just how clean and elegant it was as a subject, the neatness of it, if you like. And then even further still, so after doing my maths degree and my PhD, the thing I like about maths now is just how creative it is, just how you can construct these marvellous imaginary worlds using it as a language, but also just how powerful it is as a language and how articulate it is and capable of really describing the world around us in a way that normal language has no hope of doing.
Okay, another mathematical body in the UK is the Institute for Mathematics and its Applications, and their current president is Nara Chamberlain. So here he is.
I'm here with Nara Chamberlain at the Centre for Mathematical Sciences in Cambridge. Nara, would you like to introduce yourself, please?
Yes, hello, my name is Nara Chamberlain. I work for Babcock International Group. I'm the Principal Consultant for Data Science and Mathematical Modelling. And what that entails means that I write mathematical algorithms that solve complex industrial and engineering problems.
Wow, it sounds impressive. So what is it that you like most about doing mathematics?
I like the challenge when you see a problem for the first time. For that first few moments, you haven't got a clue what to do. And then it's the case of actually you're engaging that problem, you're attacking that problem, and I like solving the problem because, like I said, the harder the battle, the sweeter the victory.
Okay, let's hear from some other mathematicians out in industry. In the next few clips, you'll hear talk of operational research, or OR. That just means mathematics. The name comes from the Second World War, when they first invited mathematicians to help them improve military operations. In particular, how to best organise the fighter aircraft to meet the threat of incoming bombers. Nowadays, however, operational research simply means using maths in industry to make good decisions. So here we go.
Building a new depot is a big investment for ASDA and can cost up to £60 million, so it's critical that we build in the right location. We do this through a large amount of modelling and analysis tools to help us understand where in the country we will be building new stores, so where that depot needs to be.
The explosive world of Formula One. High speed, multi-million pound racing technology.
In Formula One, we require more and more expert on kind of risk analysis and game theory and simulation.
Formula One, where split-second decisions are the difference between success and failure. And often these decisions are a matter of mathematics, resting in the hands of some of the world's finest operational researchers. This is St George's Hospital in London. Here, using OR techniques can literally be the difference between life and death.
One of the really big things that hospitals have to think about is how long patients stay, and so therefore how many beds and how many wards and how many doctors you have to look after them. It's really important for us to be able to get as far as we can the right capacity for the patients who are going to come through the door so that we can give them the treatment that they need when they need it. Patients, when they're referred by their GP, either into A&E or into outpatients, enter a series of queues, and one of the things that we really have to do, and we've been working very hard on, is getting those queues as short as we can and making sure that we don't have bottlenecks in our system. And so therefore we need queuing theory and operational research techniques to help us make sure that we can get that right.
What we produce here are big steel coils that we sell on to various companies that produce everyday objects such as tin cans, office furniture, cars and fridges. The OR team currently consists of 12 members. We provide an in-house service where we incorporate ourselves into various project teams for all the departments. We use lots of software within the department where we can build real-world processes on a computer screen and visually show these to the project managers, the process specialists, and they can play out various scenarios without having to work them out on real-world processes. This in turn can save a lot of money and is a lot safer in the long run.
Maths at work is somewhat different than maths at school. You're not given a structured problem. You get a general problem, you have to structure it into a math problem and then solve it. And also the decision and result you come up with is actually used in real life decisions.
But we don't just want to talk about maths, let's do some maths too. If instead you actually want to see some more jobs, you can skip forward in the video. But here is a map of the Isle of Man showing the major towns and the distances between them in miles along the roads. Now you are a mathematician in industry working for a cable TV company, and they want to lay cable alongside the roads to connect up all the towns. But laying cable costs money, so they want to lay the least cable possible. Now, head office has come up with the plan shown here to lay cable alongside each of the roads marked in blue. Their total length, if you add them all up, comes to 76.9 miles, which you can check. But they have asked you to see if you can come up with anything better, since they know you have studied maths. So, can you do better, and what's the best you can do? So, pause the video and have a go. Okay, the answer is that yes, you can do better. Well done if you found a better solution. What we'd like to know is what is the best possible? And the answer to that is 53.3 miles. So well done if you found that, in fact double well done. And if you want a simple way to always find this minimum length connected network, if you've got some map and some island, then you can look up the algorithm called Kruskall's algorithm. It's a simple way to do it. A bit of terminology you may encounter is this minimal length connected network is called a minimal spanning tree, or an MST. So that's what Kruskal's algorithm does. Okay, let's look at another job now. What about animator? What do they do? Well, here is Shrek, Donkey and Puss in Boots from the movie Shrek 2. Now, I hope I'm not going to burst any bubbles by saying Shrek is in fact not a real ogre. He's computer generated. The artists who created him used the magic of maths to create the way he looks and the way he moves. What sort of maths did they use? Well, here are some answers. If we look first at the right, where we've got an image here, you can see the basic idea of animation is that if we have a picture of a character and we associate with a point on that picture some x, y, little x, little y coordinates, then if we recalculate the positions of these to being big X, big Y, some other point, then we can create the illusion of moving the character, or the character moving. Now, if you actually want to try the detail of this, take a look at the worksheets of the presentation I mentioned in the footer, Chris Budd's Maths Goes to the Movie Masterclass. So have a go at that. From that talk, I've taken this quote from a chap known as Tony DeRose, who was the head of research at Pixar. Now, Pixar are the people who brought us The Incredibles and Lightning McQueen and Monsters Inc. And you may have seen Disney's latest animation, Soul, about the jazz pianist. And what Tony DeRose said to people who want to use maths to work in computer animation was to learn as much mathematics as you can. Okay, and in particular, they're counting on their next set of employees, which could be you, to tell them in the future how to do it better, to tell them what maths they should be using. So that's another job, computer animation. What I'm going to look at now is a set of 4 jobs which illustrate a theme. So climatologist, biostatistician, politician and civil servant. How do they all use maths? Okay, well, a biostatistician will conduct tests and analyze data to find out how effective a medicine is. So during the COVID pandemic, it was the biostatisticians who worked out how effective the new vaccines were. But it's the politicians and the civil servants who have to decide on the basis of that information what to do in terms of producing an effective vaccination program. Similarly, if they want to tackle any other problem, for instance, maybe tackling poverty in Wales, they're going to be guided by the data on where they need to take action. So they need to understand mathematics. Okay, what about climatologist, or as we might call it, climate scientist? Similar to a biostatistician, they are an expert producing models and data to try to guide the actions of politicians and civil servants. Okay, so looking at that further, I'm not sure that anyone who's looked at the data disputes that the climate is changing. It's just a case of measuring and seeing that the global average temperature has been slowly rising, and the ice caps are melting and the sea level is rising, or that there's more carbon dioxide in the atmosphere. In fact, since any time since in the last 800,000 years, where these earlier dates, they've done that looking at carbon dioxide in ice cores. And this file, which I've taken from climate.gov in the US, it's a couple of years old. I think the current figure from the Hadley Centre in the UK in November 2020 is that we're now at 413 parts per million, but you can see it's higher than it has been historically for a long time. And virtually all climate scientists agree that humans are the cause of climate change. The figure I saw was there was 97% agreement among them. So in order to plan what we're going to do to avert catastrophe, we need mathematical models of climate. And if you want to find out a bit more about them, I'm going to recommend another talk of Chris Budd's Mathematics Climate Change there, where he looks at the climate change models. Also, if you're interested, there is the profile of a lady called Claire Burke, who studied astrophysics at Liverpool and was leading a climate research team at the Met Office. So that's on mathscareers.org.uk if that's something you want to find out more about. Okay, so that's another set of jobs. Another set of jobs is the engineers. So engineers are big users of maths. If they build a bridge, they want to know it's going to stay up, an aeroplane that it's going to fly, a computer that it will work. And to know this before they build them, they use maths to analyze and communicate their ideas. So here's an extract of a video showing engineering in action. There isn't a voiceover on this one, so just sit back and enjoy a sample of the things you could create if you were an engineer. Okay, there are lots of other interesting jobs here. So, for example, a meteorologist predicts how likely you are to have good weather. An actuary predicts how likely you are to crash your car or have your house burgled, and therefore how much insurance you should pay. A national security analyst predicts how likely we are to suffer a terrorist attack and what we should do to avoid it. They all use significant amounts of maths. And if you go on to work in any business, in fact, you'll be interested in the size of your market, the costs of what you do, the price your customers will pay, and your net profit that you're going to make. So it's a less intense use of maths, but it's maths nonetheless. So the answer to the first question, in which jobs will maths help you, is almost all. And maths is particularly useful in the jobs you see here. Okay, now we can look at a second question, which is, in which subjects will maths help you? In which subjects will maths help you? Well, the answer here is similar. The correct answer is lots. So Einstein was well known as a genius, but even he was amazed at the fact that maths is so effective in science. He said, how is it possible that something you invent in your head, in your mind, works so perfectly to describe natural reality? And it's not just the sciences. Here's Abraham Lincoln, the US president, who was a lawyer. Now, two interesting facts that not many people know about Lincoln are, one, that he campaigned using the Welsh language, and a second is that he carried a copy of the geometry book Euclid's Elements around with him in his saddlebag. He wanted to know how to prove things clearly in court, so he turned to the people who are experts at logical argument, of proving things clearly that they're true, which is the mathematicians. So maths helps with lots of subjects and not just the sciences. But one reason that maths is so important in science is that it's what's called unreasonably effective. Once you learn an idea, you will find it applies again and again. So, for example, if we take this example of exponential growth, this ski ramp, or something called exponential decay, this idea crops up in physics as radioactive decay, rates of reaction in chemistry, early stages of disease spread in biology, algorithm analysis in computer science, capacitor discharge in electrical engineering, concentration of drugs in the bloodstream in medicine, and also in compound interest and discounted cash flows in economics and finance. So you get masses of mileage out of your mathematical ideas. Okay, time for another maths interlude. This letter E here actually stands for a number, like pi stands for the ratio of the circumference of a circle to its diameter, so about 3.14. Well, E stands for the number 2.718281828459045235, and it goes on forever, just like pi does. It's named after the Swiss mathematician Euler, who lived in the 1700s, and it crops up in surprising places. So, for instance, what's the chance when you thoroughly shuffle a deck of cards that every card is in a different position to the one where it started? So in maths this is called a derangement, and you can calculate this probability for yourself for a deck of 2 cards or 3 or 4 or 5, and what you'll find is that for a deck of 4 or more cards the probability is very close to 1 over E. Another example, here we have a hanging chain from 2 posts. It looks a bit like a parabola, but it's not. It's a curve called a catenary, and the equation of that curve is roughly written as e to the x plus e to the minus x. So e is cropping up again in an obvious place. Okay, thirdly, let's have a look at money. So here I've got a £1,000,000 note. You don't see many of them, and that's partly because these notes, which are called giants, are only used internally in the Bank of England. How much interest would you earn if you deposited £1,000,000 and every year it earned a millionth of the total deposited, and you repeated that compound interest for 1,000,000 years? Well, the answer is you'll get roughly E times as much. So E is a number which crops up unreasonably often, and it's a number you're going to see more of. Okay, so we've done 2 questions. What jobs is maths useful for? What subjects does maths help with? Time for a third question. Why do employers want mathematicians? And by mathematicians, I mean anyone with math skills. That is, if you do maths, you're a mathematician. So you are all mathematicians. Well, it's because they have superpowers, what I've called here. So they're good at understanding data and at spotting patterns. They're great at solving problems and thinking clearly. If you remember, that was why Abraham Lincoln was interested in maths, so that he could argue things through clearly, and they're good at working systematically. So if you study maths, these will be your superpowers too. And furthermore, because not everyone has learnt these skills, employers value them highly. So in our society, jobs using maths tend to be well-paid ones. Okay, we've looked at 3 reasons for studying maths: the interesting jobs it leads to, the other subjects it helps with, and the important and valued skills it gives you. But there is another great reason for doing maths, and that is it can be interesting and fun. Okay, so I've got one example here, and I promise if you keep the faith and follow through to the end, you will find it interesting. So here's a procedure that you're going to choose a constant C. So for example, we could choose 1, and then we're going to start with the number 0, and we're going to keep generating a new number by squaring the current number and adding C. So for example, if we start with 1 as our constant and we start with 0 as our number, we square 0, add our constant, which is 1, to give us 1, square 1 to give 1, add our constant to give 2, square 2 to give 4, add our constant 1 again to put it up to 5, square 5, add our constant to take it up to 26. The next one's going to be 6, 7, 7, and you can see that the sequence is going to get bigger and bigger. It keeps on getting bigger and bigger. It's unbounded. However, that's not always the case. If instead we took C to be -1, then something different happens. We start with 0 again. If we square it, we get 0, and we add -1, so it takes us to -1. -1 times -1, minus times a minus is a plus, so that gives us +1. We add our constant in again, and it takes us back to 0. So if we rinse repeat on this cycle, we're going to get 0, minus 1, 0, minus 1, 0, minus 1. So it's going to go on forever like that. So this time the sequence is bounded. It doesn't tend towards plus or minus infinity. So what we've seen is that for c equals 1, the constant equals 1, the sequence unbounded. For c equals minus 1, the sequence is bounded. And the question I want to ask you is, can you find any other values of c for which the sequence stays bounded? And in fact, in particular, can you find the set of values for which the sequence stays bounded? So you may want to pause the video and investigate that a bit. The answer is, if c is greater or equal to minus 2 and less or equal to a quarter, the sequence will stay bounded. What we're going to do now, though, is develop a new system of numbers. Could we make the points on the plane behave like numbers? So to do that, we need to be able to do maths with them. We need to be able to add them, and we need to be able to multiply them. So adding them is quite straightforward. We just take the x and y coordinates and we add the x coordinates. So here 1, 2 plus 3, 4. We're going to do 1 plus 3 to give us 4, and 2, 4. 2 plus 4 to give us 6, so it takes us to the point 46. So if we add the point 1, 2 to the point 3, 4, we get the point 46. Something to note is that the origin, the point 0, 0 in this arithmetic, behaves like the number 0 anyhow, that if we add it to a point, to 1, 2, then the point 1, 2 doesn't move. Now, multiplication we're going to do in a somewhat surprising way. Okay, so we're going to define multiplication that if we have 2 points we want to multiply together, so 1, 2 and 3, 4, we multiply the x coordinates and then we subtract off the product of the y coordinates. And then for the y, so in this case 1 times 3 minus 2 times 4 gives us minus 5. For the y coordinate we're going to do the old first x coordinate times the second y coordinate, and the old first y coordinate times the second x coordinate. Add them together to give 10. Okay, now you may be thinking, why on earth have we got such a crazy way of doing multiplication? Well, what you might think of, why don't we just multiply the x coordinates, make the x coordinate, and multiply the y coordinates to make the new y coordinate? That isn't as good. I mean, the answer is, what do we want from our multiplication? And one thing that simple way of doing multiplication will have is that we could multiply two non-zero numbers and make 0. So that's something we don't like in multiplication, if we multiply non-zero things and get 0. This multiplication also has an interesting property, which is that if we define the size of one of our numbers, so the size of a point, the magnitude of a point, to be the distance from the origin, a question to investigate is, how does the magnitude of a product of points relate to the magnitudes of the individual points you're multiplying? So how does the magnitude of a product of points relate to the magnitudes of the individual points that you're multiplying? Okay, I'll leave you to investigate that. That should show something interesting up. But I'll ask you just to take it on trust that although this looks strange, this is actually a very sensible way, a good and sensible way of multiplying numbers. Let's ignore, don't worry about the detail, but let's just make a few observations. So a first is that if the y coordinate is 0, then the arithmetic is just like you'd expect, it's normal. So 3 0 plus 4 0 gives us 7 0, so it's just like adding normal numbers. And simply if we multiply them, 3 0 times 4 0 gives us 12 0. So the normal numbers, what mathematicians call the real numbers, are here on the plane on the x-axis, those numbers for which y equals 0. So 3, the number 3 is very like the point 30, the number 4 is very like the point 40, the number minus 1 is very like the number minus 1, is like the point minus 1 0. And in fact, if we have a look at that, minus 1, so the point minus 1, 0, has a square root in this new system. If we multiply 0, 1 times 0, 1, we get the point minus 1, 0. So what we have here is a set of numbers that we've created called the complex numbers. Now this is not the normal way probably of introducing them, and I haven't given you much time to explore them, but hopefully you can see that they might be interesting. In fact, they are very interesting, and we can use this new system and do the same procedure, the old procedure. We could take choose a point, C is going to be our constant, and we start with the origin, which is 0, and we square it and we add C, and we square it, our new number, and add C, and ask the question, which values stay bounded now? Which values stay bounded now? And this is a surprising answer, because the values which stay bounded, where the sequence stays bounded, are the values with a colour black here. Values which are coloured black. This is something called the Mandelbro set, and the ones which have a non-black colour, the colour is chosen according to how fast it tends towards plus or minus infinity. Now this set, called the Mandelbro set, has an interesting property, or several interesting properties. It's a fractal, which means it's got sort of infinite levels of detail. So if we zoom into this gap here, we're entering something which is known as Seahorse Valley. That's because if you look at the patterns, you've got something which looks a bit like a seahorse. And if we zoom in on those islands, then we get this pattern here. And if we zoom in on the center, that little dot, we find out it looks something exactly like a sort of baby Mandelbro set. So this is a very interesting and surprising object, and it can be shown that all the black bits are connected. So there's somewhere between this and the main body is a very thin black thread connecting it. Okay, I hope by now I've convinced you that there are some really good reasons to study maths further. It's useful in most jobs, it's helpful in many other subjects, it gives you superpowers that employers need and will pay for, and it can be interesting and fun. Okay, in the second part of the talk, I now want to look at 3 more questions. So if you are going on to study maths, what are the options for studying maths further? What topics will you cover? And how to find the entry requirements for a university course that might be of interest to you.